My name is Scott Rumschlag, and this is a measuring device that I built. It measures points in 3D space. In order to do that, you need an angle, and a distance from your origin. It's super simple. This seems like a sort of thing that you could just throw together and everything would be fine. Well, it took me about 500 hours to get this device built and go through iterations and figure out where the bugs were. And the accuracy level that I wanted to get to was about 1 millimeter at 6 feet away, so a 6-foot radius. That's what I wanted my error range to be. And I pretty much hit it. It's a touch over on a couple things, but regardless, what that means and the way I determine that is that you have this device here, and then perpendicular to it you have a line. You measure a bunch of points on it, and then you best fit the points that you calculate from this. And the maximum deviation from that, the worst one, was 25 thousandths. So then you would know that that could be either plus or minus, gives you about 50 thousandths range. So this is a 51 thousandths drill bit right here, and I'm going to hold this just a little over 6 feet, about 2 meters away from the camera. So if you use this device to measure, you can tell within the size of this drill bit, if you can even see it, where that point is. You're probably wondering what use case motivated me to invest all this time and money in a project, and it's a familiar one. It's remodeling. If you knew exactly what you needed to build, exactly how big it had to be, the profile of the perimeter, what shims were necessary to make it sit dead level, you could shift a lot of that work off-site, get it fabricated, and just bring it in, drop it into place, and be done. All the seams would look good, everything would just be done. It removes the requirement for on-site work, which is where your labor is very expensive and your efficiency is low. It's just a compounding problem. So the use case would be that this is in some sort of room or nook or whatever, and you're measuring out from a central point to various points out there. You need to be able to indicate that point and measure its location. There's some other strategies that I've tried before, like lasers. I used the Vive positioning system for their VR thing, and the problem with that is that it's very indirect. You're relying on several layers of abstraction in the math and the positioning of the sensors versus the beam sweep and the distortions and all of that. You can see my 3-part video series on it and all the time I invested in that. I did some experiments before that also with ultrasound, and ultrasound is actually much better than you might think on positioning. It's just very variable depending on temperature, and you can have temperature differences between even the floor. I can feel right now my knee is quite a bit cooler than my head is, and then up at the top it's a lot warmer. There's other things out there too, like LiDAR, which is getting super popular right now, but the problem with that is that when you're basing things on time of flight, there's really very few systems that get better than a couple millimeters, because you have to get into things like femtosecond timing and all of that. There's reflections, the problems that you have with lasers, and you just get a colossal amount of data also. What you really need in a situation that I'm envisioning for this is something like maybe 30 points. So 30 sets of coordinates, if they're 32 bits each, that's 360 bytes of actual data that you want. Okay, that's your foundation. And if you did some basic scan, I mean, I've heard some of these things are gigs and gigs, right? So even one that's 500 megs, if you were really looking for 360 bytes, that is 99.99993% waste. Something like this is just very efficient because you're indicating exactly what you want and nothing else. Also, by going with the cable strategy, this thing is accessible for my level of resources. A couple other good things about this is that there's really no interference. We don't have wind inside, and all the errors are very consistent, so you can characterize them, you can figure out what they are, and they tend to be extremely repeatable. And what this means, between you indicating directly what you want, so you're using the human to filter the data that you're gathering, and this very direct system is that we have a high confidence in our measurements. Cable systems like this have been out there for a while. They've actually been out there for decades. You can read various things on them and see them from all kinds of different companies. But a lot of them, they're extremely expensive. It's just absurd to me. I mean, I just couldn't stomach it. So they're too expensive, even if you buy them old and used. And I said, hey, this one's simple enough. I'm going to build it myself. So let's talk a little bit about resolution requirements. If you want to be able to discern a 0.5 millimeter 3 meters away from you, that's going to require you to divide a circle into about 38,000 different points. So when we're looking at encoders and you see different ones advertised as high resolution, oh, high resolution, yeah. Okay, well, and then they say 2,400 points per revolution, or 4,000, or 10,000. You get a sense here already that we're not even close to that. So you have to go out and look at encoders. There are some things you have to keep in mind here too, like whatever resolution you want your ultimate measurement to be, your device has to be maybe an order of magnitude better than that if you can. That's a nice rule of thumb that they use in metrology. You may not hit it, but that's what we want to aim for. So 38,000 separate points, boy, if we could head in the direction of 380,000 points, that's more what we need. There's different types of angle encoders. Some of them are mechanical. That's not good because I can't have any drag here. When I move this thing here, even just the tiniest amount, several feet away, way back here, if I move that just a little bit, I need this to follow. So I cannot have any drag there. The bearings need to be low friction, they need to be low stiction also, and my encoder ideally would have no influence on it at all, and that's why I went with optical encoders. Magnetic encoders are also non-contact, but they're not totally linear. By a couple percent, or maybe even a little bit less in some cases. But guess what? A couple percent of, 1% of 2,000 millimeters is 20 millimeters, right? It's a huge error. So a couple percent is enormous in this case. We can't handle that. I went with optical. Also, optical has very low noise, at least for this one. You can use almost all the bits on it. This is a 17-bit encoder. If you go onto Mouser or DigiKey and sort by most bits, you'll find one on there, which is, I can only imagine, is a joke. Basically, on the data sheet, this is what, as Dave Jones would say, this is what happens when you let the marketing people take over. It says 39 bits, and that seems pretty high. It seems a lot higher than all the other ones. So if you actually read the data sheet, it has two modes. There's a 23-bit mode for single turn, and then a 16-bit multi-turn. Therefore, of course, you have 39-bit resolution on your encoder. And if you're not into this sort of thing, this is like having a house with a 3-story section and a 2-story section, and you're asking how many stories is it, and the realtor says 5 stories. Well, it doesn't quite work that way. So 39 bits, you can't trust that one. Even the 23, it's mechanical. If you actually read through the data sheet, it has however many hundredths of a newton of torque. Not going to work for this. The encoder down here on this spool does not have nearly as strict of requirements, and that's because this diameter is much smaller. This one is about 1,000 pulses per revolution. What you do have to do is you have to measure directly on the drum, however. If you try to wrap it around a pulley that turns with it, even that very small amount of slippage will screw things up. So you have to measure on the drum directly. You need to make sure that your tension when you're winding it is the same every time so that it rewinds exactly the same. If you can pull that off, you get super repeatable linear measurements with these. There are cable transducer measurements, or whatever they're called. It's escaping me at the moment. But you can buy these things off the shelf, but a lot of them only have like a 2-meter range, and they use potentiometers for their distance, so their linearity isn't as good. I put rather a lot of time into building this thing, a lot of time, and I looked around to try and avoid doing that, and I just settled on the fact that I had to build my own. One of the most difficult parts was the spring here. This is actually a tape measure spring that I pulled out. Getting it mounted just right was a little bit tricky. I bought some retractable cords that you can use for extension cords, those reels. I bought dog leashes that have springs that come back automatically. I bought all kinds of different springs and tried to experiment with those. The problem is that you need many revolutions. If you want to have a great big drum, you could maybe get away with a couple, but your tension's going to climb rapidly. I want to have relatively constant tension over many revolutions, and I also want to avoid tension hysteresis as much as possible, where it's going to change depending on if you're coming or going, because that changes my correction for the cable droop. No matter what you're doing, gravity is bringing you down, and you have to compensate for that because it causes the boom to point at the wrong spot. So ultimately I ended up threading this thing here with a little custom tool that I ground, and having that cable lay in there. I'll throw in some close-up shots. Error separation was a major challenge here. Just visualizing the error is difficult, because if we're talking about a 2-meter measurement and you're trying to nail down that last millimeter or two of noise, it's very small. You can't just plot these things and say, great, there it is. I can see obviously that, you know, the square isn't square, or the circle isn't circle, or circular, or whatever. So what I ended up doing in a lot of cases was having that shape that I was looking for, calculating the difference between the measurements that came out of this and what I thought it should be, and then multiplying that by 50 or 100. And that allowed me to actually look at the points and say, okay, there's a pattern here of something going on. 0.5 millimeter also at a 2.5 meter radius is 200 microradians, or about 1/100th of a degree. So when we're talking about these errors here and you're trying to decide what sort of things that could contribute to the error, I mean, we are talking about everything. This thing is bouncing back and forth just a little bit right now, right? I mean, that's completely swamping the resolution that I need if it doesn't settle towards the end. So everything is a concern when you're trying to figure out what's wrong with it. And in order to find these errors, you have to be able to calculate them, which seems self-evident, but it's a little bit trickier than it sounds. One of the ways that you can do this is by taking a bar of known length, or of any length, as long as it doesn't change, and putting it in different orientations. So putting it in front of the device, putting it vertical, diagonal across, behind. There's actually an ASME standard for this, and just if you're curious, it's B89.4.19, 2006. That's actually for laser positioning systems, but it's set up in a very similar way. And the reason why we don't actually care how long the bar is, I mean, within reason, I think they use one that's about 2 meters. So I actually have this bar, which is 30, I stamped it on here and I machined the ends. It's 36.5 inches long, and then I have another one which is 83 inches. And the reason why we don't care is that if your system works, you should get the same measurement in various orientations. So whether this is 36 or 39, who cares? It's really just a scale factor. So the problem with using this as a method of trying to figure out where your errors are is that it's very time consuming to mount it in different orientations, and you only get 2 points. which doesn't really tell you anything about the pattern of distortion that you might be getting. So what I settled on was using circles and lines. So the great thing about a circle is that I have my rotary table for the milling machine. You can attach an arm to it, attach this to the end, and then take it around the circle and trigger points. And you know that you should get a circle. You know that you put a circle in, the size is irrelevant, you should get a circle out. So whatever points that you calculate, you can best fit a circle to those, and then look at your deviations from that. This is what I was referring to earlier. You can do it with lines also. And the great thing about lines is that you can sort of sit on an axis and measure that and see what you're getting. So what kind of errors was I trying to find? Basically what had happened was that when I would measure a line in front of it, I would get this bouncing pattern, kind of like a very noisy parabola. And when I would measure a circle, it would almost seem like it was measuring too far into the circle, and then it would come out. And I made a lot of plots trying to correlate it with tension, and I just wasn't coming down and being able to figure out what it was. The things that I had to consider was everything. Like I mentioned, we're talking about hundredths of a degree here. So you have to correct for the origin, because your origin is the points where your axis of rotation this way and the one this way intersect. And this actually changes depending on where it is here. So you have to correct for the offset origin. You have to make sure you're starting in the same place every time, which is why I have this screw here. So I know that I start here, and then I have a correction for gravity, because I need to know when it's horizontal, because then gravity is going to be affecting the string perpendicularly. There's cable stretch, there's the change in the spooling path length here, because this is changing. So there's a triangle, it's going from a certain offset to a smaller amount. There's flexing of this frame potentially. What I did was I mounted a mirror on here, and I had a laser pointer that was bouncing off of it back onto a wall a long ways away. And then when you pull on this with varying amounts of tension, you want to see if that mirror leans and that your laser shifts. You could see it shift. I determined that it really wasn't significant, and that was not my source of error. But that was much easier than doing some fancy thing with an indicator that might actually influence it, since I'm looking for very small changes. There's perpendicularity of the axes also. I have a shaft here which it rotates about, and then there's a shaft here. How do I know that these aren't set up at some sort of angle? I mean, I know they're not perfect, and I surely did my best, but you have to figure that out, and you have to correct for it. This is the sort of thing you can use the reversal method on, where you go across center and you look to see if it's tilted one way or the other. You can correct for that. I am doing it in this one on the math on the back end. I forget what the number is. I can put it up here, but it's a very small amount that I found to help. There's the spring action of the wires that are coming down the center from this second stage axes. I mean, I bought some of the smallest silicone insulated wires I could find on McMaster. They're, I think, 32 gauge wires. They're very small, they're very flexible, but they have some spring action on there, and you know, I couldn't figure out what the problem was, so you had to consider it. There's bearing drag also. How do I know that this thing isn't dragging like this and then dragging like that, right? There's the catenary droop of the cable. The further this thing goes out, the more it sags. You have to correct for that. Mathematics errors, right, also associated with that. I was trying to do the corrections on the Arduino Mega so that it could directly output XYZ, and at one point I had started calculating some of the corrections on my computer, and it seemed like it was going good, and then I transferred that code over to this and it just wasn't working. It was really bizarre, and it had me scratching my head, and then I realized if you look up the floating point precision of the Arduino Mega, it wasn't high enough. The way that I was solving the problem was iteratively, and if you want to iterate, you have to look at very small changes in an already very sensitive number, and then iterate, based on that. So you end up needing a couple orders of magnitude better than even your dimension that you have. I mean, keep in mind here, if we're talking about fractions of a millimeter at 2-3 meters out, right? That's several digits of precision that we actually require. You add on top of that, you run out with this thing. I think it has 6 or 7 digits of floating point precision. So my iteration thing was running, but I was getting weird results. So I actually had to stop running the correction software on the Arduino Mega and switch it to my laptop where I had more bits available. There's also always the problem or the potential that my circle that I'm inputting to this thing is not a circle, that there's something funky going on with that. In metrology, they call these artifacts, okay? So maybe my artifact has something wrong with it. It's flexing. Maybe my line isn't a line, right? So maybe my distortion that I'm seeing is not a problem with this, it's a problem with that. Hysteresis, like I mentioned, with the boom oscillating and maybe settling or sticking in different positions. What if something's dirty? If this thing's out of level also, if it's leaning like this and this isn't balanced about this axis, maybe it has a tendency to lean this way here and then that way over there. So as you can see from this small list, there's a lot of things to consider, and then they can have interactions, and you just have to consider all of them and try and figure out what's wrong. Basically, I had a subtle math error in the way I was calculating the catenary correction, and I won't go into it here unless people want to hear about it more later, but I had a small error there, the sort of thing that you think wouldn't matter that much, and it turns out that it does. I also had my angle correction between here and horizontal was off by a little bit. And what that means is that gravity was pointing the wrong way for my correction. This is separate from the other math error, so they're both related to the catenary droop. Catenary meaning this, well, if this cable had enough weight to overcome the ribboning effect from being under tension, the droop that it would make, like a chain or something like that, under its own weight, different than a suspension bridge cable. So basically gravity was off slightly, which means that the catenary droop was being corrected for incorrectly. On all of these topics here, believe it or not, I have actually abbreviated this immensely. I could go on forever. I don't want to overdo it 100%, but if there's something in particular that people have an interest in, like the encoders or the way that this is set up, some of the other things, or the math correction, I could certainly make a video about that. I also thought that, some other people might be interested in making one of these, and if there was any interest in plans, I would certainly be willing to hear that. It's not especially complicated to make. There's just a lot of decisions that have to be made, and you need to make them correctly in order to get the accuracy out of the system. I've already worked through a lot of those bugs, so it would certainly be fairly easy once I've set that path for someone else to follow it. I've estimated that I could build this for around $400, probably a bit less depending on compromises that you might make. So it's a pretty affordable thing, and you can get very accurate measurements out of it. There's a lot of systems that you see and they say, oh, millimeter level accuracy. Well, that just means that they're going to state the error in millimeters. Okay, so 5 millimeters means that it's millimeter level accuracy. Come on. This is true sub-millimeter accuracy across a wide volume. I'm going to maybe goof up the numbers here. I didn't put it on my notes, but I mean, if you think about a cube, this isn't the part I'm going to goof up, but if you think about a cube that's a meter on each side and you want to have 1 millimeter resolution on that, that's 1 billion points. Okay? 1 billion points in just a cubic meter that you need to be able to discern. And then you've got to go, 6x that if you want to go half millimeter. If you have a so many meter radius, I'll put the numbers on the screen right now, but you have a certain radius and you're not going all the way to vertical and you're not going all the way down. But if you divide that out, I worked out the math, and it came out to, for the working volume of this device, about 710 billion points that you need to be able to discern between. And that is what really makes you appreciate why all these little things matter, is because we're trying to reach out there and put our finger on that point, and then this one, and then that one over there. I mean, everything has to be right. You can't fudge it. If you want to be able to measure between points that are over there and points that are over here, you can't do it with some inertial system and lasers and, well, in this one case it was kind of accurate. No. You've got to have a system that sits here, your base doesn't move, everything is rock solid. This is why you look at CMM machines and they're all on granite blocks so that everything is very, very stable. Another thing about this that could go wrong is that if you're on a floor that's flexible and just the weight of the person operating this thing, or someone stands near it and causes this thing to lean just a little bit, it's going to throw things off. If you really want to measure things, you have to take all of that sort of thing into account. So this project was very challenging. It was fun to share, so thank you for watching.